Hello, my name is Grzegorz Ćwikła. I'm from Silesian University of Technology. I'm going to talk about similarity of parts determined by semantic networks as a basis for manufacturing cost estimation. All we know that companies are forced to compete on global markets, and one of elements of to maintain competitiveness is the speed of response to the offer query from potential customers. And we can use two main groups of preparing of offer for production of mechanical parts, and some of them are more precise but slower, and we can also have simplified methods that are based on experience on production of similar components. And we are going to use this second method. So in the past we used this method for determining production cost of shafts, and now we have made an attempt to use it for a selected group of gear housings. So in this article we modified this method to include those selected group of gear housings, and to run some tests on this method on those elements. So we have a few assumptions of this method. First is that production cost of new element is similar to other previously manufactured elements, assuming that those elements are similar enough to each other. Usually we don't have CAD models of new elements, and it's time consuming to prepare one, so we want to avoid this. But we need, in order to use this method, we need the extensive base of previously manufactured components with calculated real production costs. And when we want to calculate, to estimate new element, we should first we have to describe it, to code it into some specific way, and then we are searching in database for similar enough elements, so we can say that if those elements are similar, its similar cost will be similar too. So this is the algorithm of this cost estimation. If we found an element that is similar, we can prepare offer. If this offer was accepted and we produce this element, this element real cost, production cost is calculated, and it enriches our database, so it is more accurate in the future. If not, we have to prepare offer with classical method, more time consuming, and again enrich this database. So what about description of elements? We decided to use semantic networks, and technology-oriented features as a way of description, and elements have to be initially divided on some classes, and we created something that we call skeletal semantic networks, allowing to describe the group of specific group of or selected group of elements. And in case of gear housings, we decided to take into account some technological features like type of gear housing, overall dimensions, weight, and expected machining, and a few others. And then we have elementary surfaces that can belong to 3 main planes, and to each plane we can attach some entities like base surfaces, diffusion surfaces, secondary positioning hole, and other, and the most important, the main hole. And each of these entities can be defined by some relative values and some next technological features. And one of those main features, like main hole, can have more, it is the most important part of gear housing usually, so it can be described with also with some next lower level features, surfaces. So this is how this semantic network looks like. This, as I said, it is divided into some levels, and describing new element, we choose between between something from this list of potential features, and we can use them many times based on complexity of element. Then we can go to assessment of element similarity. We use this similar method like last year. We are comparing semantic networks describing specific elements, so corresponding branches of networks are compared. We have a set of equations allowing us to calculate similarity in from 0 to 1 range, when 1 means that elements are identical. So as I said, we have this equations, and based on this partial similarities, the overall similarity of whole pair of elements is calculated as average value with some weight factors. Those weight factors are important because we can change the weight of some specific features on overall results. So after calculation, we have this overall similarity. Then to validate our method, we took a set of real elements from one of producers, and we proposed the real production cost similarity factor to verify this structural and technological similarity. And here are the equations allowing to calculate this factor. So we calculate structural and technological similarities between all elements. We calculate cost similarities between elements, and then we are checking if there is high convergence of both results. That means that system of cost estimation work properly. So the corresponding values should be similar. So as I said, we have 16 elements, test elements. Each of them is somehow similar to this one. This is very simplified description of those elements, so I'm going to skip it. We have also this real cost calculation of our example part based on material cost, labor cost, and other parts. So we can calculate total cost, real cost of these elements, and then we can calculate both structural technological similarity and cost similarity. So we can say that if those values are similar, it means that also cost should be similar. So we run a few sets of calculations, and in first all weight factors were set to 1, and results were that only very high similarity meant that cost similarity also is high, and then it started kind of jumping. So in second set of calculations, we changed some weight factors to get much better result. Sometimes those changes appear to worsen the results, like in the 4th series, and in 5th series we got results that are good enough to say that this method of cost calculation should be accurate enough. So we can say that this method of cost calculation and cost estimation should be good enough for our application for early cost estimation of elements with enough accuracy to prepare offers. Thank you for your attention.